Welcome to ECE 302. This is lecture 6.2 on characteristic functions. I'm Professor Stanley Chen. In the previous lecture, we learned about the moment-generating function. It is a very useful technique to handle a sum of two random variables or more random variables. In today's lecture, we're going to learn a variant of that, which is the characteristic function. What is the characteristic function? The characteristic function is defined as the expectation of e to the power minus j omega times x. If you compare this definition with the moment-generating function, you realize that I am really just substituting s equals to minus j omega. Here, j is equal to the square root of minus 1. This definition tells us that I am evaluating this s not over the entire complex space, but I'm only looking at the imaginary axis. So s can go over the entire complex space, but then for j omega, you're just looking at the y-axis. So what is this? This is indeed the Fourier transform, because this you can write it as the integration of e minus j omega x, and then you have fx dx, where this fx is your PDF. If you go to the library, you grab a textbook on probability, it is very likely that you will see another definition of the characteristic function. In those textbooks, people define the characteristic functions with a plus sign instead of a minus sign. Both definitions are correct, because if you're evaluating your moment-generating function on this vertical line, you can start from the bottom to the top, or you can start from the top to the bottom. Both will evaluate the same y-axis, and therefore both definitions are correct. We choose to follow this, the first one, because it is more consistent with how we learned the Fourier transform in the Signals and Systems course. So how do we understand the characteristic function? As I said, the characteristic function for a PDF is really defined as the Fourier transform. As a result, what you can imagine is that if you have the z equals to random variable x plus random variable y, then the characteristic function of z of j omega would be equal to the characteristic function of x j omega times the characteristic function of y of j omega. This is really consistent with how we understand the Fourier transform. If you take the Fourier transform of x and y individually, you multiply them, you will get the Fourier transform of z, and that is equivalent to taking the convolution between the two PDFs. The table here gives you the commonly used Fourier transforms, and you can also find the same table in our course website. In what follows, I will talk about several examples to make sure that you understand how to use this table and also the characteristic function to solve some very difficult problems. So to start with, let me talk about this example where you have a random variable x defined with this PDF, and you want to find the characteristic function of this PDF. So we can start with this PDF. This is e lambda x. This is your fx. We know that when you take the Fourier transform of this PDF, you will get the characteristic function. This characteristic function, of course, you keep this lambda here, and then there is e minus lambda x. It turns out that this, you go to the table, the table would be this expression. Here it should be a plus, and then this one should be minus. You have this e to the power minus a times t. Well, of course, you can translate this a times t to lambda times x. That will give you 1 over a plus j omega. So you have 1 over lambda plus j omega. and therefore the characteristic function of this PDF x is given by this expression lambda times lambda times 1 over lambda plus j omega, which is this. So this is actually very easy. You go to the Fourier transform table and pick up the right equation, and you will be able to find the characteristic function. Let's work on a slightly more difficult problem. In this case, I have a pair of independent random variables with individual PDFs given as follows. I want to find the PDF of z equals to x plus y. Now we know how to do this problem using convolution, and I believe that you have suffered of doing this exercise. Now I want to show you a shortcut using the characteristic function. First of all, we recognize the characteristic function for this PDF. The characteristic function for x of j omega is lambda divided by lambda plus j omega. This is just following from the previous example. Similarly, for characteristic function of y, it is given by the same form. And therefore, we know that the characteristic function of z is the product of the two. So you have lambda divided by lambda plus j omega, this entire thing square. And so as long as I can take the inverse Fourier transform, I will be able to get the PDF. So the solution of this problem is given as follows. You have the characteristic function of x, characteristic function of y. That comes from the transform table. And then you take the product of the two. That is because the two random variables, they are independent. And therefore, when you try to find the characteristic function of the z, that will be equal to the product of the two individual characteristic functions. You multiply the two together, and then you have this form. And in this form, you can go back to the table. So here you have lambda square times 1 over lambda plus j omega square. You go to the table. The table will say that if you have this expression, then you have this as the original PDF. And so you plug in the values, then you can show that this will give you z times e to the power minus z. Now, this is not t, right? It's z because I'm looking at the PDF of z, and therefore I replace all the dummy variables with z. Let's work on another example. This is the third example. Here I am defining a sequence of random variables with all these PDFs. It looks very complicated, and furthermore, I want to define this y equals to the infinite sum of these random variables. I want to find the PDF of y. Okay, so how do I find the PDF of y? We know that the characteristic function of y is the characteristic function of x1 times the characteristic function of x2 times dot 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 times the characteristic function of you have infinitely many of those, and so you have xn, j omega, and you keep continuing. And you don't just start with 1, you start with 0. So you have 0, 1, 2, and so on. And then for each of those, you know the form. This is ak divided by lambda and ak squared plus x. So we know how to do this because we can go back to this equation here. We can find out the corresponding Fourier transform, which in this case it would be this expression. Alright, so we can take the Fourier transform. So we can take the Fourier transform to get some expression, and then take the Fourier transform to get some expression. And since they have some form, and then you will need to multiply them together. And then afterwards, you will take the inverse Fourier transform to get back the PDF of y. So that would be the flow of this exercise. Okay, so exactly how do we do this problem? Well, let us go to here. You have this expression. This is ak divided by lambda of ak squared plus x squared. this, I need to take the Fourier transform. So let's go back to this table here. If you have a squared divided by a squared plus t squared, that would translate to pi a e minus a of omega. Okay, so let's bring this expression down here. So you have pi a e minus a omega, and that is true when you have a squared divided by a squared plus x squared. So let me just double check to make sure that this is correct. Okay, so if this is the form, then we know that this is the Fourier transform. Now the difference between this and that is that here this is not in the form that you want. So I need to put a square here, and I want to divide by 1 over ak, and so this will give me pi ak e ak and then omega. And I should not forget this expression, which is that I also want to divide by this pi ak. Now this divide by pi ak comes from here. You have this ak and then there's a pi that will correspond to these two numbers. Okay, so let me just recap. You have this a squared divided by a squared plus x squared. You take the Fourier transform, you will get to this form. Now, in order for you to take the Fourier transform of this guy, you need to scale them properly so that it will take the exact same form as what you have over here. And in order to do that, I will have 1 over pi ak that comes out. And so that will give me this expression. And then this expression, when you take the Fourier transform, you will get pi ak e minus ak, and then you have omega. Alright, so you can see that this the Fourier transform of this guy, you can cancel out these two terms, and so the Fourier transform is as simple as e to the power minus ak times this absolute omega. Alright, so we have found the characteristic function of xk of j omega, which is equal to this expression. And so the characteristic function of y is just the product of all these terms. So you take the product of k going from 0 to infinity of e minus ak of omega. And that is exactly the same as e to the power minus omega when you have this infinite sum. And then you can calculate the infinite sum. This infinite sum is just summing over all these 1 over 2 to the power k plus 1. That is given by your problem. And remember, k has to go from 0, 1, and 2 to infinity. So when you plug that number in, you can show that that will sum to 1. And therefore, your characteristic function of y, with this term goes to 1, you will only have this e to the power minus absolute of omega. Then you take the inverse Fourier transform. The inverse Fourier transform will tell you that this is going to be 1 over pi, 1 plus y squared. And therefore, the PDF is given by this form. So as you can see, the flow is actually quite simple to understand. You start with the individual characteristic functions, you multiply them, you get a characteristic function of y, and then each individually you can find using the Fourier transform, you multiply them, you take the inverse Fourier transform. So that is the flow of how do we calculate the PDF of y. Now, you may ask, why do we want to use the characteristic functions while we already have the moment generating functions? The reason is that the moment generating function is not always well defined. For example, here I have a Cauchy distribution with the following PDF. We can show that the moment generating function of this x will go to infinity, whereas the characteristic function is a well-defined subject. That's why people prefer to use the characteristic function, because they do not need to worry about the existence of the moment generating function. Here is a proof of why the moment generating function of this random variable x, this Cauchy distribution with this PDF. This PDF doesn't have a moment generating function, and we can do some calculation. So this is the moment generating function of the Cauchy. So you have this e to the power sx, and then here is your PDF. You're integrating this function from minus infinity to infinity, but this is really bigger than if you integrate from 1 to infinity, because both terms are positive, and so now you're integrating a smaller range, and of course you will get a smaller integral values. And then here you have this e to the power sx, but e to the power sx is what? Is 1 plus esx, 1 plus sx plus sx squared divided by 2 plus sx cubed divided by 6, and so on. So this is the exponential Taylor expansion, and since every term is positive, then of course it will be bigger than just one of those. Okay, and so now if you're bigger than one of those, then you have this hold, and so it will be bigger than you can substitute this number here, so you have sx cubed divided by 6. And now you have this sx cubed divided by 6, then what? Well, you can do some simplification. The simplification is that you have this sx cubed, and then you have this x squared plus 1. But hold on, this sx squared plus 1 is actually this entire thing. Okay, so this entire thing is bigger than or equals to sx cubed divided by 2 of x squared. Why? Because if x is bigger than 1, right? So you have x bigger than 1, then the x squared will also be bigger than 1. That is the range of your x, and therefore this number, so the x squared plus 1, has to be less than or equals to x squared plus x squared, which is 2x squared. And so you have this expression here. You have this to the power 3 divided by x squared plus 1. It will be bigger than or equals to this with the 2x squared. And then now you can cancel out all the terms. Then you have s to the power 3 divided by 12 pi. And this is the interesting term. So you have x. And then your x is integrating from 1 to plus infinity. And you know this is going to plus infinity. Therefore, your moment generating function is bigger than infinity, and therefore it is undefined. So for this particular Cauchy distribution, we know that the moment generating function is not defined. However, when you try to calculate the Fourier transform, you go back to the table. The table will say that if you're looking at a Cauchy distribution, which is this distribution, the Fourier transform is indeed well defined. Okay, and therefore, if the Fourier transform is well defined, that means you have the characteristic function. The characteristic function is there. This is exactly the reason why evaluating along the imaginary axis is easier than evaluating over the entire complex plane. So to summarize, I think we have learned this characteristic function through various examples. It is a very useful technique for us to deal with a sum of random variables. The characteristic function has a good linkage with the Fourier transform. Indeed, the characteristic function, if we define using this way, the expectation of minus j omega x, this is exactly equals to the Fourier transform, which is integration of minus j omega x and the fx x dx from minus infinity to infinity. So you have the Fourier transform, and therefore we can use the Fourier transform to do the calculation. So I hope this lecture has taught you something interesting and useful, and you can easily extrapolate this idea to n random variables. And as we can see in the previous example, having this tool in hand, that can simplify us a lot when we deal with the sum of n random variables, where originally we need to take the convolution infinitely many times. So this is the end of today's lecture. If you have any question, please let me know. I would be very happy to help you. Thank you very much.